Okay, so let me retake where we left, or a little bit before we left. Okay, so let's recap a little bit what we are doing. I will make a slightly different construction of the P-invariant measure, just to make sure we did some details correctly, and it's also a good discussion. So let me remind you, we have gamma mod n acting on x to the alpha. Gamma is a lattice in G, not on x, I'm sorry. We call it alpha, and instead of considering the action of this quotient group, we just look at the action of gamma itself on x, which is n is in the kernel of alpha. So then it's pretty much the same. And then we do this suspension construction, which is G times x quotient by the relation, where we do Gx, we relate with G gamma alpha of gamma inverse x. Now G acts here in this space by right multiplication. We still call it alpha. A star Gx is, or left multiplication, Ag x. And we want to now start with a P-invariant measure for this guy. So P here is, let me just do it in short, maximal amenable group. Actually, what I'm going to construct is true for any amenable group, but I prefer to start with the largest possible. That's why I'm taking it maximal, and it's pretty much this MAN, where A is diagonal, N is upper triangular with 1 in the diagonal, M has plus minus 1 in the diagonal. So we are looking for this P-invariant measure, and for this I could do what I try to do, but then there are several details I should be more careful about. So this is what we called X alpha. And one of the definitions of amenability will allow us to just build this P-invariant measure on x to the alpha as soon as x to the alpha is compact. But x to the alpha fibers over G mod gamma at the same time that G times x fibers over G. So this projection on the first coordinate goes to the quotient. And this G mod gamma may not be compact. And once this G mod gamma may not be compact, automatically the X alpha cannot be compact whenever this guy is not compact, because the image of compact is compact, and this is a non to map. So in this case, one goes more to the point and do a more explicit construction, and then it will be completely clear that the measure is actually Haar down here. So what do? I will do the following. I will define a compact convex space. I could do it in two different ways. I will finally do it in one very explicit case, but in the meantime, I will build the two constructions. So let's call P lambda X alpha, which is a set of probability measures on x to the alpha, such that, and this projection is pi, and this projection is also pi, pi star mu, so probability measures mu, pi star mu equals to lambda. So the ones that project to Haar measure. Okay. And actually, this is a construction which is very useful in more generality. So here everything is, so X is compact metric, G mod gamma is a beautiful manifold which is metric, even if it is not compact. So the total space is still metric and locally compact, and then you have the notion of Radon measures and blah, blah, blah. But once I ask there that the measure projects to lambda, I'm saying that I don't care anymore about the quotient space, I only care about the fiber, and the fiber is a compact metric space. So actually the base could be a very general measurable space with some measure, and still this guy here will be a compact convex space. So this is lemma. This is compact convex. Okay, now I could define somewhat different space. P lambda x. Now it will not be probability measures, but it will be Radon measures, and it could be more explicit later, but in this setting, Radon measures will do. So a Radon measure is a measure which is finite on compact sets. Okay? Mu on G times X such that pi star mu equals to lambda. Now this automatically will tell me that if I fix some compact set on G and I look at what's going on in the fibers essentially I will have, if I look to Rokhlin decomposition, I will have probability measures. Okay? Because it has to be finite measure in all, and it has to project to the Lebesgue. So the measure of all these guys will have to be the measure of the base. So which means that you need to have ones up there. Anyway, so I have these Radon measures. Now this space is also compact and convex, by the same reason above. So of course I should put a distance function or a topology on this space. So this is naturally a subspace. Maybe just this is naturally a subspace of all. Okay, the P maybe of all measures, all Radon measures on G times X, which is naturally the dual to C0 on this space. Well, it's not just C0, it's C0 with compact support. Okay. And C0 with compact support, it has naturally a structure of, well, metric space, and more importantly, a structure of locally compact, not locally compact, locally convex vector space. So it has a natural dual, it has the weak whatever star topology, and this is the natural topology here. And with respect to this topology, which is the same topology as always, so you are convergent as soon as when you pair the measure with a function which is compact supported, you have the convergence. Then if you put this guy, this topology up here, you get a compact metric space up here, which is not hard to see, because if you take mu n, a sequence of measures, then you take a family of compact set Kn containing K, union of Kn, in G, union of Kn equals to G, so an increasing union over there, and then you do mu n restricted to KL, you extract the subsequence here, Qni, which has a limit, mu L, all these measures here project to Lebesgue on this compact set, so the limit will still project to Lebesgue on this compact set. Then you just increase the L and do a diagonal argument and take a sequence of measures which are defined on every larger and larger, and at the end you have a well-defined measure which project to Lebesgue and is clearly the limit over compact sets. So this tells you that this is a compact and certainly convex set. So in general, you don't have this nice compactness on space of Radon measures, okay, because you have the most important problem is what is called the escape of mass. So when you are in Radon measures, you could go to infinity, so the mass of the measure could be happening close to infinity, and at the end you are losing measure. So that's the big problem when you deal with Radon measures. But that's exactly what we bypass by saying that the measure projects to Lebesgue. And once the measure projects to Lebesgue, the only possible escape of mass would happen from G, and the measure projects to Lebesgue, so there is no escape of mass along G. So it can only escape along X, but X is compact. So then there is nothing to worry about. Okay, so so this tells me that this guy is a compact metric space. And very good point, very good point. Very good point. It will be more non-trivial in the next step where I'm going to discuss. Yeah, it's non-empty because you just take Lebesgue measure on this set. But then in what is coming next, what you just said is a very non-trivial statement. Well, maybe not very non-trivial, but it is more non-trivial than here. So next, I take this guy, which are all the measures mu in the previous guy, such that alpha gamma star, let me call it this way, star mu equal to mu. Okay, where alpha gamma of Gx is what was there, G gamma okay, so it's the measures that actually come from the quotient space, from the X alpha. Now, this is naturally a subset of this. It's naturally convex, and it's naturally closed. So it's a compact convex set as before. Now, what is a little bit less trivial is it is non-empty. So we have to produce one measure there. And this is a very important step. So how we build a measure there? Well, is not the silly thing of putting the x naught. Where was the x naught? I erased it. Oh, it was here. Okay, it put Lebesgue measure here, so I cannot do this anymore because this will not have this alpha gamma invariant. So I need, in a sense, a graph which will be alpha invariant. That's what we are going to do. We are going to build a graph which is alpha hat of gamma invariant. And for this, we take sigma inside G, fundamental domain, for gamma. So it means that gamma is for L measurable, not gamma, sigma. Actually, it will be a closed, well, not closed, but a semi-open, semi-closed set. Actually, I could take it open if I only were mod 0, doesn't matter. So sigma intersection sigma gamma empty for every gamma not identity, and the union. So that's a fundamental domain for us. And then we do similar as before. So we take on sigma times x naught, we take lambda times delta at x naught, and then on sigma gamma times alpha gamma inverse of x naught, we take lambda times delta at alpha gamma inverse of x naught. So we put these measures, so it's actually sum, so mu with gamma in gamma of there lambda restricted to sigma gamma times delta at alpha of gamma inverse of x naught. Okay, so this measure will have the alpha hat invariance, and the reason for that is that alpha, gamma star lambda restricted to sigma is lambda restricted to sigma times gamma. So this right invariance property of the invariant metric of the Haar measure, which is also left invariant, so it doesn't matter much for this point, tells me that this measure mu still projects to Lebesgue and is alpha hat invariant. So this measure mu belongs to this guy. So it's non-empty. So this guy is non-empty. Okay, good. So it's non-empty, it's compact, convex, and I have P acting in G times X by this left multiplication here. So P star Gx is P Gx, which this action is actually the one that projects to P star Gx equals to this guy. But in any event, I have this action here, and this induces an action on this m lambda times m alpha g naught times x, which is an affine action. And by one of the definitions of amenability, whenever I have an action on a compact convex space by affine maps, it has a fixed point. So we have a fixed point. P star mu equals to mu for any p. And also, by definition, I know that this is alpha gamma star mu equals to mu for every gamma, just because it belongs to this space, and as well P star mu equals to lambda. So it projects to lambda. Now I can do Rokhlin decomposition theorem, and again, Rokhlin decomposition is in reality for probability measures, but it works as well for Radon measures. Just pretty much the same thing we did before. You take the sequence of compact sets giving you everything, and you apply Rokhlin to each of these guys, and everything will match.
So this mu is essentially
this one, yeah.
Yeah, it is is the joining of Lebesgue on gamma and delta measured along an orbit.
Yeah, that's pretty much. Yes, that's pretty much what it is. So it's a step function. Okay, it's not really a G orbit, but it has the gamma. It is with a gamma orbit. So
yes.
But yeah, you're right. So if you project to x, you get the orbit of x naught, the gamma orbit of x naught. If we project to G, we get Lebesgue. So it's a joining between these two guys. Absolutely. And actually, it's very important that you call it a joining because we are looking for a joining from x and G. Okay? Or something as close as we can. Okay, now Rokhlin theorem. Essentially allows us to disintegrate. So we have x, G in G mapped, or maybe let's G in G maps into mu sub G, and this is a probability on G times X, which we identify with probability on X. And modulo this identification, so this is a measurable map. And it's this identification from G into probabilities of X that we call phi. Phi of G is mu sub G. Okay, or to be more explicit, well, actually, that was correct, is delta at G times phi sub G is mu sub G. Good. So this is the phi function, and the phi function will inherit these three properties. So let me be explicit on what does it mean to inherit these three properties. So 1, phi is defined lambda almost everywhere on G. So this is measurable and is defined almost everywhere with respect to lambda on G. And in general, with respect to whatever measure you are projecting on G, which is lambda. Second, alpha gamma star mu G is mu G times gamma. And this is how this alpha hat business is going. Or equivalently, yeah, maybe I should use phi of G here. Phi of G gamma. And 3 is phi of P times G is phi of G. So this last property is actually telling me that phi is in reality a function coming from G mod P. And here you see why I told you in the very beginning, when it comes to the game, P will be quotient on the left and not on the right. And it's because the invariance comes from here. And this property here gives me the equivariant, so I have the natural gamma action here by right multiplication, and I have the gamma action here by pushing measures, and this is a conjugacy. Okay? And now comes the theorem, which is Margulis Factor Theorem. Says the following. Let's see. Okay. It actually doesn't even require this to be a compact space. Just Borel measure space. So it says the following. So assume gamma, the lattice in G as before, gamma acts on a space C measurably so there is a sigma algebra on C and gamma respects this sigma algebra. There is no measure so far here. Let H from G mod P into C be a measurable map defined lambda almost everywhere. So I have lambda is Haar measure here, and this measurable map is defined lambda almost everywhere. That's it. That's the hypothesis. So this is what is called a factor of, oh, I need one more hypothesis so that it becomes a factor. So I need the dynamics here and dynamics here to be pretty much the same. Okay? And this is what is called a factor. So let's put it here. Can I write here and here and it's okay, good. So and assume H of P G gamma to be gamma star. Maybe let's call this alpha. We always call these guys alpha. Alpha of gamma times H of PG for every gamma in gamma. So this is the conjugancy property. Okay, I have the gamma action on the left, I have the gamma action on the right, and the H permutes I have alpha of gamma, I have the multiplication by gamma here, and it does the commutative diagram. And again, this is for every gamma in G and almost every G P in lambda in P mod G. Okay, notice that I don't need really to talk about any measure on Z, just the sigma algebra. But once I have this map H, I can push Lebesgue measure here to measure in C. So there is no harm on pushing this measure down there. Really doesn't matter. Okay. So maybe let's put this a name. I wanted to say something else as well. Oh, one more thing is, especially I don't want to introduce a measure here because whatever measure I put here will not be gamma invariant. And especially will not be gamma invariant because there is this H. And the lambda here is not invariant by the gamma dynamics. So that we saw before. So then this is not about invariant measures, even though there is some invariant measure behind as we want to see. But okay, so let nu be h star lambda. So now I project this measure on Z, and then the point is that there exists a map. Maybe I should have called this guy instead of h phi. So now I need a new letter. Eta. Why not? Even though eta, I will leave for the gammas. Alpha, beta, rho, f, g, h, iota. Hard to have a short alphabet in life. Okay, but k then I use it. Let's call it psi. Not nice, but still, it's something. It's a letter. So psi, well, there is, first of all, there is Q closed subgroup of, so that's what is called a parabolic subgroup. Whenever you contain P, you are called, and are closed, you are called parabolic. And psi from Q mod G with lambda into C with nu, an isomorphism. So this means that is bijective almost everywhere, brings measure lambda to nu and brings back nu from lambda. So that's an isomorphism, and which is also natural. Okay? Such that the following commute which means I have P mod G, I have Q mod G, just put it down. This is the natural projection because P is inside Q. I have H here into Z with nu, and I have psi here, and there was lambda here and lambda here, and everything commutes. So I have the alpha action here, and I have the gamma acting here and gamma acting here. So this is the natural projection. So this downside arrow is natural. So which means that this factor is in a very natural way isomorphic to this action. So it's not just isomorphic to this action, but it's isomorphic in a way that it's respecting the previous factor I was having. Okay? So when I do this isomorphism with this and this, the H becomes this projection. When I do this identification here.
And psi is also unique.
M?
Psi, the isomorphism.
And yeah, the isomorphism is essentially unique. Yeah. Yes. So that's Margulis Factor Theorem tells how the factors of G mod P look like. So there are some natural factors which are all the G mod Q. These are all factors of G mod P. And that's nothing else. So that's all. These are finitely many. As we saw, what are these possible Qs? So you have the P, which is the upper triangular matrices with whatever you want in the diagonal. And then you can keep on adding guys by putting some staircase in these matrices, and this completes the group. That's it. Nothing else happens.
Oh, I guess in the SLN case, it's not that new of a statement. Like you can compute everything, basically.
Yeah, exactly. So there is no much, but that's also true in any simple and even semi-simple group. So it's very easy to compute these guys, the G mod Q. So they have these combinatorics. So you have this root decomposition, you have the Dinkin diagrams, and then it gives you some order among the roots, and it's telling you whenever you put this, you have to put that, and other than that, you are free, and blah, blah, blah. So it's some combinatorial problem, which is not really very complicated. Let me add here. So G has to be semi-simple and rank as at least 2, and gamma irreducible lattice plus you don't want factors being SL2 for this guy, or even, well, there are several cases. Let's say, I guess just gamma being irreducible and G being higher rank is good, but as always, in our case, we do SL in R, N at least 3, and that's all we care, okay? Gamma a lattice. Okay, so that's the theorem we are going to show in the next 2 weeks. Let's see why this theorem actually solves all our problems for Margulis Normal Subgroup Theorem. Okay? Well, we will not solve all of them. We'll solve 95% of them. We still will need to talk a little bit about property T at some point. So let's see. What do I want to erase here? I have this. Yeah, but I want to keep this statement, so I guess I erase up there. Okay. So claim either N is a subgroup of the center of G, or gamma mod N is amenable. Okay, proof of claim. Well, I prepared the whole business for the proof of the claim. Okay, so we take X compact metric, alpha, gamma acting on this compact metric space, gamma mod N, I'm sorry, acting here, and I want to build an invariant measure for this guy. Okay, then I have induced from here this action alpha of gamma till mod N on probability measures of X. This induce gamma acting on these probability measures of X so that N is inside the kernel of alpha. And this is now Z. So we saw by the previous construction, so this is phi up there. This measurable map defines G almost everywhere into this P of X. We satisfy the hypothesis of the guy. So this H is the phi. So the commutativity of this diagram is condition 2. The fact that it's defined on G mod P is condition 3. The fact that it's well defined with respect to lambda almost every point here is the condition 1. So I am in the hypothesis of the guy, and the thesis of the guy tells me that then this guy via psi is the same as G mod Q with respect to some measure here. So there will appear some measure here, nu, which is just push lambda by phi, and I have this isomorphism and this projection. Okay? Now, what is very important here is this isomorphism now, because I know that N is inside the kernel of alpha. This will imply that N is inside the kernel of this guy. So this is equal to the kernel of gamma acting on G mod Q with respect to the lambda, so we have to be a little bit careful here because everything here is measurable. So here I'm thinking of this as a measurable action. Okay, so an action by measurable maps. So more explicit, these are all the gammas in gammas such that gamma QG gamma equals to QG for almost lambda almost every QG in Q mod G. Okay, so it's enough to be equal to the identity lambdas almost everywhere to be in that kernel. Different from this previous kernel here, which was a topological kernel. Anyway, doesn't matter because multiplication by gamma is continuous. So if you have equality lambda almost everywhere, lambda is fully supported, this implies equality everywhere. Okay? So the first thing is I can remove the lambda almost everywhere without any problem. In any event, this is inside, naturally, a subgroup of the, how should I call it? A. In G, such that GA equals to QG. For every G, or for every QG in Q mod G. And now this is the kernel in G of the action of G on Q mod G. So this guy in the right-hand side is a normal subgroup of G. So this group A in G such that QGA equals to QG for every QG in Q mod G. This is actually normal in G. Okay, so once it's normal in G, G, remember here is SLNR. In the simple case, it's the same. In the semi-simple case, one have to work a little bit more than this, but let's not do that. Then either this guy is inside the center of G, actually is equal to the center of G, or Q equals to G, and this guy equals G. Okay? Now, in the first situation, I get N is inside C of G. That's what I wanted. Okay? So let's assume by contradiction that N is never in Z of G. So then I will show that gamma mod N is amenable. So no by contradiction. Then 2, I get that Q has to be equal to G. But Q equal to G, what does it mean Q equal to G? It means that Px, comma, nu, this is equivalent to G mod G, comma, lambda, which is delta at identity, or G times identity, what is this? G space comma, delta at G identity. So it's a one-point space, which means that, of course, P of x is not a one-point space, but the measure nu is concentrated on a point. So it means that nu is delta at some nu naught for some nu naught in P of x. And I have the alpha gamma invariant property there. So I have then that phi of Pg is equal to nu naught for almost every G. And then the alpha of gamma invariance tells me that alpha gamma nu naught equals to nu naught for every gamma. So I get my invariant measure. So that's the proof of the claim. So either n is in the center or every action of gamma mod n has an invariant measure. So I assume by contradiction that n is not in the center, and I took an action of gamma mod n, and here is the invariant measure we needed to construct. Settled. So let's see how is our timing. 2 more minutes. Okay, let's use 2 more minutes. And so we are not going to prove the theorem in 2 minutes, but let me tell you in 2 minutes how we completely finish the normal subgroup theorem once we have this claim. And then on Wednesday, we start preparing for the proof of the main theorem. I only will prove it in the case that C is a compact metric space and the gamma action on C is continuous. This is not really such a limitation, because any measurable action is essentially continuous if you do it in a correct way. Yeah, let me mention that for this part of the theorem, actually, we will see, so the normal subgroup theorem, GA being SL2 cross SL2 and gamma being what is called an irreducible lattice, it's good. So, and that's all we needed to show this claim up there. Okay, so the claim about normal subgroups. So this amenability.
So I have a question. So,
Yes.
where does this assumption that n is not in the center come into play?
Oh, because I get that this kernel is either in the center or Q has to be G. Okay, so I need to do some contradiction. It's not 100% needed, but if not, I have to do contradiction every time in a sense, or a dichotomy every time. So, because I have to prove the existence of the invariant measure for every action. Okay, other way of doing the contradiction would be, okay, assume it's not amenable, then there is an action without an invariant measure. Then I get this action alpha without the invariant measure, I do all this construction, I reach this level, and then if Q were G, I get an invariant measure. So Q cannot be G, and if Q cannot be G, then this guy is the center of the group, and N is inside here. So that would be. It's really not needed a contradiction. I don't like to use contradiction when it's not really needed, but in this case, epsilon helps the logic, but it's not really needed. Okay, so what I need to do, which I will not be able to do it in 2 seconds, but still, is discuss a little bit of what is called property T. Kazhdan property T. Oh boy. Okay, hope it's correct. Property T. Because Kazhdan was the one introducing it. It's a very strong condition on a group. It's amazing he came up with this condition because it's so good, so useful. It's just 3 Chi's paper where he proved everything that needed to be known. So it's wonderful. But anyway, so the point is that the groups we are dealing with has property T. And property T is the complete opposite of amenability in a sense. So it's one of the ways you can think of it. Is similar to amenability in the sense that it's a property that has infinitely many different definitions. It's a property that is inherited by quotients, by some subgroups, depending on what you are assuming, or actually more than subgroups. When you increase your group, is inherited, and all this stuff. So what we need to know is the following. One, let me just do the definition. So G, as always, locally compact, Hausdorff, second countable, has property T if every continuous unitary representation with almost invariant vectors has a non-trivial invariant vector. Okay, so corollary of the definition is that assume G is amenable and property T, then G is compact. And if G is discrete, then G is finite. Okay, and the proof is just put both definitions together. So you take your action of G on L to G. This is a unitary action, continuous. Amenability tells you that this has an invariant vector, and property T tells you that once you have this invariant vector, there is a non-trivial invariant vector. Now, a non-trivial invariant vector is a constant, by definition of the action here, which you can assume is a constant 1, which means that 1 is in L2. So it means that the Haar measure is finite, and finite Haar measure means that the group is compact. That's it. So that's how we are going to prove that gamma mod n is finite. So once we prove that gamma mod n has property T, we are done. So let me just state the claim, and we finish. So claim gamma mod n has property. Then we are done. So the corollary then gives you gamma mod n is compact. And that's the statement of Margulis Normal Subgroup Theorem, and the proof of this is in 3 steps. One is SLNR has T, property T, if n is at least 3. Is not true when n is 2. Second, if gamma is G, so lattice, and G has T, then gamma has T. And third, if gamma has T and n is normal in gamma, then gamma mod n has T. Okay, so these two properties are completely general. Lattices in property group T groups has property T. Quotient of property T groups has property T. SLNR has property T. actually is the most important case for this matter is SL3, and from SL3 you get SLN, and the SL3 case, and actually the SLN is what Kazhdan proves in his original paper, and is one of the nicest proofs still. So I probably will not discuss much yet this property T, though it's very important, and I plan to discuss it, but I want to focus on the normal subgroup theorem first, on the factor theorem first. So next Wednesday we do the factor theorem. Okay? Okay, thank you all. See you on Wednesday. Okay, so we are back. So we have to prove this Margulis Factor Theorem. So let me remind you what it says and how the proof starts. It will not be, I guess, very surprising how we start. Then we will stop and I will do a digression proving a theorem that may have nothing to do with this factor theorem, but my goal is to try to convince you that they do have a lot in common. So we have this gamma acting on this space C. As I said, in the general measurable situation, there is a way to end up with a continuous mapping. So I will be assuming that this is bihomeos. C is compact metric. And actually, in the case we care, C is the probability measures on a compact metric space. So it is compact and metric. And the action is as well continuous. So it's not a problem. Gamma is a lattice in G, and G is SL and R, and at least 3. And then we assume there exists the following diagram commuting G mod P into Z. Here we have the gamma action, here we have the gamma action here, and the diagram commutes. This is H defined lambda almost everywhere. Okay, I think I'm not missing anything. Or gamma lattice, of course. Okay, yes, I think that's all the hypotheses. Yeah, yes. H measurable. So then there exists Q closed, which means parabolic. So that's the definition of parabolic, closed and containing P. Such that the following diagram commutes G mod P, H, Z, G mod Q, and gamma, gamma, gamma. This is the natural projection, and there is this isomorphism phi. From isomorphism, actually, I want here Q mod G lambda Z nu, and where nu is H star lambda. So we project nu from here, from the lambda Haar measure here, and then these two spaces are isomorphic by phi. This phi as well conjugates the gamma action here with the gamma action here, and that's it. So meaning, so once I have this, I can essentially assume that these two guys are the same guy, and they are the same guy in a very natural way, meaning that this pi is still the projection from here to here under this identification. So the H becomes pi.
And I guess Q is also unique up to conjugation.
Yes, Q is unique up to conjugation. Yes, that's, in a sense, is part of the, well, maybe it requires some extra effort, but yeah, it's, yeah, I think it may not follow directly from this statement, but it's not such hard an effort. So it's just the fact that G mod Q and G mod Q prime are not isomorphic if Q is not conjugate to Q prime, especially not. So in this setting, it's much simpler because it's not naturally isomorphic, because this isomorphism we have to respect pi to enter into this business. So oops. So the fact that this is not possible should be reasonably easy to prove, but actually, unless Q and Q prime are conjugated, actually they, yeah, you still some, you have some, wait a second. Yeah, you can make the conjugancy to respect the projections if Q and Q prime are conjugated, but other than that, if you remove this, this is still also true that I think that they cannot be conjugated just without any pi. Well, actually, if they are isomorphic, then you put this isomorphism into this picture, and then you end up having the natural isomorphism, and the natural isomorphism makes them conjugate. And so, yeah, essentially, it's a nice exercise. Yeah, you're completely right. So it's non-trivial, but it's only one. Okay, we have to prove this statement. Okay, and to do this, we will undo a little bit of the construction we did to reach this statement. Okay, so we will take G mod C, G times C, and do our relation GC related with G gamma alpha gamma inverse C. So alpha is this gamma action on C. And then we have this G action on this, we call this C alpha. Oops, no, that's not C alpha. With quotient by derivation, and this is C alpha. So we have this G action now in C alpha. Okay, we came from here actually to build that. So actually Z was X. Now I'm doing it on this C, which was supposed to be P of X, but still, this is very similar to where we came from in a sense. And now, when we were discussing it before, we built a P-invariant measure coming from some amenability. Oh, okay. Come, Nawaf. Yeah, I guess. Yeah. Okay.
You cannot hear, right?
Yeah, now I can hear, but then I have echo.
Thinking about this theorem, so the biggest thing really, you're only promoting P to a kind of closed that's really what you try to do.
Oh, wait. Okay, let me mute and then I am mute. So P is closed, so I'm promoting to to a larger Q, and from a factor I'm getting an isomorphism. So this H is not one-to-one at all, and I'm making it one-to-one. So it's really the isomorphism. Okay? Okay.
And so it's essentially a statement about the fact that the quotients, the factors of this G mod P carrying this gamma action are
Just
these
exactly. Exactly. So from a measurable perspective, so you have, yeah, maybe let's discuss epsilon this. So you have the notion of conjugancy or isomorphism and the notion of factors. And you could define an action's alpha smaller than the beta if, say, alpha is a factor of beta. And this defines an order. Okay? Now, on this relation, I could quotient the actions by isomorphism. And if I quotient the action by isomorphism, I still have the order. Now it will really be an order. Oh, okay. So you make this relation of order by alpha being a factor of beta. And this is true for in any setting. So you fix the group and you define this relation for these actions. Now, to make it actually a complete order relation, you just quotient by the isomorphism relation. So then if alpha is smaller than beta and beta is smaller than alpha, then they will be isomorphic, and hence, well, that's not trivial, actually. That's not necessarily true, actually, in full generality. So even that is not fully a relation. But anyway, so you still can quotient by the isomorphism property. Now, what is this theorem telling us is that this set of actions, when you are looking for the ones below G mod P, so it will be this set, essentially. So meaning all the guys smaller than G mod than P mod G. It's just a finite set, and it's a finite set determined by this G mod Q. And the order relation restricted to this guy is realized by the projections, the natural projections from the fact that P is inside Q or so. Okay, so that's what this is telling in a sense.
And do you assume that H is essentially bound-to?
In a sense, you are assuming it tacitly, because when I say an isomorphism, I'm putting the measure nu here, and the measure nu is nothing but the push of the lambda. So I'm only seeing the piece of C that is seeing the measure, the image of H. So I'm not seeing anything else than the image of H. So I don't need to assume it, but in a sense, I'm doing it. And actually, when it comes to application, if you remember how we apply, we have Z being the set of probability measures on X, which in principle is a huge space, but the measure nu becomes delta at a measure. So the image of H is just one point in one of the applications, which is the invariant measure for the gamma action on X. So that's how you get, which is the smallest guy here, is the point action. So yeah, the goal here is to get this Q. The Q I already defined, I will remind you, but it's very easy to find the Q. what is very hard to prove is that for this Q, H is an isomorphism. Okay? But the Q itself is really not hard to get. Actually, maybe before I continue with this, let me define the Q very explicitly, and then Q will be clearly a group, not so clearly closed. We will see then by this construction why it is closed, and after we know how to prove it's closed, then we will have to develop the machinery to show that H is actually, well, the phi naturally created this way is an isomorphism. And the phi actually is like there, it will go from here to here. So what I'm going to do now is, as I said, define Q, define phi, and then I will prove that Q is closed, and then it will take me 2 weeks to show that this phi is an isomorphism. So all the rest I can do it fast. So let me define Q now. It's really easy. Q is all the G's in G's such that phi of, let me see if I'm writing it correctly. Yes. P, G, okay, let's call it A. A, G is equal to phi for almost every G in G of P. Okay, so let me give you a second definition of Q that will be a little bit cleaner than this definition. So let me define phi. Oh, phi is H. Thanks. So H hat, see if I define H hat from G into C, so the natural map H hat of C is H of P times C, or of G. Okay, just I'm pushing it up. So this is H hat, this is H, this is pi into G mod P, this is H, so just the composition of these two guys. Then I'm taking Q is all the A's in G such that H hat for almost every G.
This is the first isomorphism theorem in some category.
Yes.
Essentially.
And clearly Q contains P by definition of H hat, because H hat of P G is H of P times PG. Now these two guys get the same, so this is, and this is H hat of G. Okay, this is whenever P belongs to P. Little P, this is P. So this shows that Q contains P. That Q is a group is essentially as well. In all these situations, you have to play with this almost everywhere, but this is just the fact that the intersection of full measure set is full measure sets, and that translation preserves the measure, even the measure class in G, because it's Haar measure. Okay, so Q is a group as well. So So as I said, that's how you define Q. And then naturally, once I know that this is Q, I have naturally defined down there, and this H still extends to a phi. So I just defined phi of QG as being H of PG is equal to H hat of G. So, and this is well defined independent of the choice of G exactly by the definition of Q. Okay, so that's phi. Now, this is not easy at all to show that it's a closed group, because you take a sequence AN going to A, and then you have the sequence of guys. H is just measurable, then you will have to work. So you can do it. It's not trivial. It can be done from this definition to show that Q is closed. I will give you a second definition, which will be the same definition essentially, and then it will be completely trivial that Q is closed. Okay? But for this I need to finish this construction. So let's define a measure on Z alpha. Okay, mu. And actually it will be a p-invariant measure, and this measure mu is the graph of H. That's what is essentially the measure mu. Okay, but then I have to make it clear, actually it's the graph of H hat in G mod Z sent to the quotient. That's what is, and then it's a very well defined guy. So let me first define mu hat on G times Z, and I will define it just by telling you how you integrate functions. So the integral of phi of GC d mu, phi a compact support, continuous compact support function, mu hat. This is the integral, double integral, well, it's just one integral of phi of G a hat of G dg. Good. So phi is well defined just by definition of Q. So the difficult thing is to prove. Okay, so I don't need to unmute myself to say that. Okay, so the fact that Q is closed is hard, so it's non-trivial, but it's not impossible. So it's what we are doing now with this construction of the measure mu and the second explanation of Q. So what is really hard is proving that the phi is one-to-one, is injective. That would really will take 2 weeks. So proving that it is closed, so proving that it is well defined is trivial. Proving that it is closed is harder, and we have to do the second construction to get it. And and proving that it is one-to-one is really the huge problem. So to prove it's closed, I'm defining this measure mu on this space, actually a probability measure. Probability measure mu on C alpha. Okay, I define this mu hat there. Then I essentially project this mu hat to G mod gamma. Okay, So how I do project it is I like to do it through fundamental domains. You could do it through compactly supported functions as well by doing some average, but I prefer to do it through fundamental domains. So we take sigma, fundamental domain, for gamma and I have this pi restricted to sigma. From sigma to g mod gamma is now both, well, Borel. So now this guy is bisection, and it's also an isomorphism between Haar measure here and the restricted Haar measure there. So I just define the integral of phi of gx d mu as the integral of phi composed with okay, maybe I need more space. I thought I could do it, but no, I need more space. Let's move it over here. It's so bad. Okay, I guess I can erase it here because this is just words that are not helping. So the integral of phi of gx d mu of gx is by definition this integral of phi of pi minus 1 of g comma x on sigma times z d mu of gx, mu hat of gx. Okay, so that's how I define it, and the whole lemma, main lemma, will claim that this is a well-defined measure. So, and the fact that this is well-defined comes from the correct choice of G. So if I want to make it, since this G is in G, so let me make it cleaner here. Instead of pi minus 1, let me put here G times gamma intersected sigma. Then it should become more clear what is this point here.
This doesn't depend on sigma.
And it will not depend on sigma as well. Absolutely. So this, I guess, there are two things to prove, maybe three. One is that it's well defined. That's not so bad. Second is that is a probability measure on a compact, well, it's not compact space after all, because this C alpha may not be compact as always because you have this G mod gamma problem, but so you still have to prove that it's a Radon measure, but that's not really a problem. It's a probability measure after all, so this will not be a problem. And the third thing, which you don't need to prove, but it's good to prove because it really makes it look nicer, is that it's independent of the choice of sigma. But again, the independence of the choice of sigma is just followed from the fact that any other sigma can be written as pasting together copies of the or pieces of the previous sigma, and most importantly that the gamma equivariance of the H. So that's all that need to be done. Okay, so in the picture is what we are doing is the following. Here we have G mod C. So let me just identify it with a line. What I did here is taking a fundamental domain for this line. Here is the quotient space. I'm just defining the measure here by taking this huge measure here and restricted to this piece. Okay, and maybe I should have said here, so that's that would have made all the other three statements I said after simpler. Is that mu hat project to lambda on G. So here this pi goes from G times C into Z. And mu hat is alpha hat of gamma invariant for every gamma, where alpha hat of gamma applied to GC is G times gamma alpha gamma inverse of C. Okay. So it's undoing all the discussion we did about measures in the previous construction. Okay? Simply remember that I started with a p-invariant measure, or not even with a p-invariant measure. I started with the action, and we discussed a lot about the measures and the p-invariant measures to build this function h here. And now I am doing all this and coming back to the action and producing the p-invariant measure just from the h. It's pretty much the same. It's a very important construction, but it's standard. So it's good to do all these exercises because it's something that is used a lot. And so it's good to just be able to play with these concepts with some ease. But well, let's define this measure mu. So let's see what can we say about this measure mu. Oh, I had this one. I should have used. Okay. Now I use it. Okay, so what we have about this measure mu? So we have C alpha projected into G mod gamma. We have this measure mu here, and it projects into lambda here. We have that mu is p-invariant. And that's because the mu comes from the graph of h hat, and the graph of h hat is naturally p-invariant because I'm just lifting this p business. And now let me say who is Q. So remember we have a G action here. Q is all the A's in G such that alpha G star mu equals to mu. So it's the stabilizer of mu. So it's the guys that leave this measure invariant. The stabilizer of mu. And now the stabilizer of a measure is naturally a closed space, just by definition of topology and continuity of this operator acting on the measures. Okay, so if Gn goes to G and alpha of Gn star mu equals to mu, then alpha G star mu is equals to mu as well, because the limit of these guys is this guy, and that's it. There is only some slight, as always, I say, subtlety, which is since the spaces we are considering are not compact spaces in principle, because gamma may not be co-compact, we have to argue that the fact that Gn goes to G implies that alpha of Gn goes to alpha of G when I pair with mu. So this is escape of mass problem, but that's why I emphasized this problem here. So the fiber is compact, the base is not compact, but in the base we always have lambda. And all these alphas, so all these GM preserve the lambda in the base. So then this is not a problem. Okay, so this tells that Q is closed, and the fact that Q coincides with the previous Q is just one computation. It's not really hard. Is the fact that this measure mu is the graph measure. So then it's clearly one is inside here, so the previous Q is inside here, and this guy you use the definition of invariance plus the disintegration of the measure plus the definition of the measure, and you get that this coincides almost everywhere, like in the previous definition of Q. So you get that both Q coincide, so we have now that Q is closed, just from this definition. Okay. We will have one next definition of Q soon. Okay? And the next definition of Q, actually, I'm not going to do this extra definition. So there is a third definition, if you want, which is the definition that appears in Margulis' original paper. Okay? Which I will not make it appear. I should talk about Zariski closures and everything. I don't want to enter into Zariski closures, at least not yet, to define this. But I will make the picture, and with the picture I will try to convince you what is the extra definition of Q. So this picture will explain in the picture what we need to prove now. Okay? So let me, before tell you what we need to prove now, and how we are going to prove it, let me tell you what we have done so far. So we found Q closed. We find phi. We didn't prove it's an isomorphism. Okay? So this phi, the way we defined, it does the equivariance property without any problem. It projects the lambda still to nu, because this is just doing not much. But it may fail to be one-to-one. So we need to show it is one-to-one. Okay. So let me try to draw the picture and see if I can convince you how we are supposed to prove these guys one-to-one. Okay, let's move up there.
As a stabilizer for some flag as well, like we did before.
Well, actually, we will go into that now, but you don't know yet what is the flag or anything like that. You see, so that's why. So in a sense, this measure mu hat we are defining there, which comes from H, is somehow identifying some flag which is stabilized. Okay, and the way it is doing it so far is by, well, destabilizing the measure mu. Okay? But we are going actually to dig a little bit deeper into this and try to see the geometry behind that. So let's see if I can really do any picture at all. I'm very bad at drawing pictures and trying to transmit whatever I want. So my problem is that I draw a picture which has two lines and I see a lot of things, but no one sees them because I just draw two lines. So that's why it's not so easy. But well, for you, not for me. But anyway, so let me try to see if I can do something. So here is C, here is G. Okay, here is mu hat. So mu hat is a measure here. Now a measure, so here part of the game is to understand that a measure is really a lot of things. So if you go to your original definition, the measure is a set function. If you think from the probability perspective, it's a probability. Okay. Now we'll try to use the measure to see some geometric perspective of it. Okay? And here we are in an excellent position to try to think of it, because we are already identifying measure with graph. So we have this measurable function h, or even the h hat now that I'm in the complete product space, and I have this graph. So I'm trying to see how nice is this graph. Okay? So let's first understand what does it mean already here. Maybe I should do it first in the G mod P. Okay, let me do first in the G mod P situation, and then I will go back to the thing, or even the G mod Q, just even better. So I have this graph. Now, what does it mean that this graph is injective? So the fact that this graph is injective means nothing but the fact that this, which I just draw, is not happening. Okay, so that's the first thing we learn in calculus, or even better, I don't know. You work at TOC, you learn it in kindergarten. But so you have three crossings, you don't want that. Okay? Now we have to look at it a little bit more careful. So what is this line I draw here? Okay, and that's what is not, well, it's obvious from here that this should be G mod Q because it's a product space, but I need to make a better sense of that. So that's why I go to G. I still have mu hat in this product space. And now I have this horizontal. Now, what is this horizontal now? So, of course, this product space is first coordinate, second coordinate staying constant, and then I cross it. Now, I don't want you to think it this way, even though I eventually want you to think that way, but by now I want you to think in the following way. So I have a G action on G times C, which is the action that goes to the C alpha eventually. And this is the G orbit of a point. Okay, so I have the partition into G orbits. Okay, now I look at the graph. Let's play with colors. So I look at the graph. The graph is something. Whatever it has to be. Now I make it on purpose not injective, because it cannot be injective, this graph, because I'm already in the product space, G times C. And the H hat, if you remember the definition of Q actually, I have that H hat of A times G is A hat of G. And that's the definition of Q that eventually allows me to make sense of phi. So this tells me that when I move along the Q subgroup, this doesn't change, which means that all these coincident lines should happen as soon as I'm in the group Q. Okay? So what I'm saying here is that the graph of H hat is Q saturated. Q saturated by this action. Good. Actually, originally it was P saturated only. I upgraded it to make it Q saturated. And the question is, can it be worse than that? So what happens with this guy? G times Z, which is actually, I want to think of this as I said, the G orbit of C, or actually of EC, say, or whatever point GC. Oops. Intersected the graph of H hat. So how is this set? Now, if I want phi to be 1-to-1, I need this set to be just Q and nothing else than Q. Because as soon as someone else other than Q belongs there, I lose one-to-one property. Okay? So this guy has to be equal to the Q orbit of GC, which is equal to QG times C, if we want phi to be one-to-one. So the only way I can make phi one-to-one is by making this equality too. Okay? So this containment follows from the Q invariance. The definition of Q, essentially, Q is the largest guy doing that. The equality is what actually we want, if we want to show one-to-one. And you can use, again, I will leave it for you as an exercise to check that this condition implies one-to-one and is actually equivalent to one-to-one of phi. So it's really quite straightforward. Now, how did Margulis define Q? So here we are approaching from inside. Margulis, instead of approaching from inside, he approached from outside, meaning that he defined Q as the smallest closed subgroup containing this guy, essentially. Okay? So that's how he defined Q. He used some ergodicity and some blah, 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 saying that this subgroup is well defined and independent of the choice of G, as soon as this is true for almost every pair GC and blah, blah, blah. Okay, and then he showed, so he had for free then the other inequality, the other containment, and he still had to prove equality. So we are doing this other way. For me, it's a little bit more natural. Certainly for Margulis, it was more natural the other, but that's what we are going to prove. Okay, so this equality here. Now for this, I need to switch a little bit some things, because I really need to play with measures, not with these graphs. And that's why I want the measure mu and the measure mu hat to be there. And I will be playing dynamics, so I need the P invariance of mu and really to play ergodic theory. So what I wrote here is a set, okay, which is this intersection of the graph, but this set carries a measure. And what is the measure? Well, let me tell you what is the measure. I can disintegrate the mu hat measure along horizontals using Rokhlin theorem. I have to make some argument to use Rokhlin theorem because mu hat is not a probability measure, and now it's really not probability. So the horizontal is the Haar measure on G, which is like Lebesgue measure on the real, so it's really an infinite measure, even though it's locally finite. On the C direction is fine, it's probability. So I have to work somewhat. It's not really so hard after all. We went somehow through it. I take a sequence of compact set, one inside the other, growing in this direction. I apply Rokhlin to each of these guys. But different from what I did before, which I was looking at the measures on the vertical. I'm looking now for the measures on the horizontal. Okay? And that's what is somewhat subtle. I have to be careful because for the vertical it was a compact space and I was looking for probabilities on the vertical, so I had a normalization which is 1. For the horizontals, I will not be getting finite measures because I already contain the group Q and the group Q is huge. So I will find some family of measures on the horizontals, which are not well defined up to some normalization. So maybe let me restate it. They are well defined up to normalization. They are not completely well defined, the same way that Haar measure is defined only up to some normalization. It's not unique otherwise. So the same thing will happen here. So I will build this measure, and this will give me measures on the horizontal. And once I have these measures on the horizontal, instead of talking of the sets, I will talk on this measure. And instead of asking this equality for the sets, I will ask equality for measures, where here is this measure given to me by Rokhlin, and here is Haar measure on Q. Okay? So that's what we are going to do. So that's the goal of the proof. So okay, so this actually brings us another observation, which is very important, which goes back to the Q invariance of the measure mu, or even for the measure mu hat for that matter. Okay, so what does it mean? What does it mean that the measure mu is Q invariant? Now, to understand the Q invariance, what I have to do is, instead of disintegrate along the G orbits, I can disintegrate along the Q orbits. Okay, so Q is a group acting on this product space, G times Z, and I have the Q orbits. It's a partition. Then I can argue the same as was arguing 2 seconds ago. You apply Rokhlin theorem, you disintegrate these measures along the Q orbits, and then you look at these measures on the Q orbits. And you ask yourself how these measures look like. Now, the fact that the measure mu hat is Q invariant is exactly telling you, and is equivalent to tell you, that this conditional measure along the Q orbits is Haar on the Q orbit. Okay? So, and the same is true for iteration of a diffeomorphism or a homeomorphism, or when you look at flows. So when you look at iteration of a homeomorphism, you are looking to a C orbit. You take an invariant measure for the homeomorphism. You do some Rokhlin type of argument. You define some measure along the C orbit. So it means that you are taking a measure on the integers, and you want this measure on the integers to be the counting measure on the integers. That's what the meaning of the measure to be invariant. Now, when you take a flow, you do the decomposition, you take conditional measures along this R, which is the copy of your orbits now, and you want this measure to be Haar measure. There will be no normalization ever, so you cannot say that your conditional measure along the flow orbits are Lebesgue whose interval 0, 1 measure 1, because this normalization you will not have it, but it's still the same measure Haar without saying which is the normalization for the measure. So up to a multiple, it is Haar measure. So the same is true for any group action. So you take a locally compact Hausdorff second countable group acting on a space, you take an invariant measure, or you take a measure, the measure will be invariant by this group if and only if the conditional measure along the orbits is Haar measure on this group. Okay? Yes. Oh, now good. Yeah, go on.
Yeah. So just maybe a premature question, but is this kind of argument very similar to, say, Benoist's arguments, or like the same in the arguments used in the same major rigidity for random surface?
There is something of it. There will be something like that. So, and yes, the punch line is very similar to that. Well, there are several punch lines in Benoist as well as here, but one of the punch lines is very similar. So you will end up having some translation invariant measure along some direction. If you have 2 points on the same whatever direction, you get this translation invariant, something like that. Yes. That's why I'm going to do some digression now and move to something completely different, essentially, from this, which is closer to this one. Actually, what I'm doing is the other component, which is Furstenberg times 2 times 3, or Rudolph actually times 2 times 3, or Katok-Spatzier times 2 times 3, and still is the same thing. Good. We are out of time. Okay. Okay. So yeah, we are out of time. So I hope the geometry of what I intend to do is somewhat clear. Don't worry if it is not 100% clear. It's never 100% clear, not for me at least. We are going to do next Friday the digression, so we are going to move to just 2 commuting diffeomorphisms on the torus T3 and prove something about measures there. And then we will try to make some abstraction of this result to a very general setting. And then we will see how this general setting, when we bring back to this type of game, tell exactly what we wanted here. Okay? Okay, thanks. See you on Friday. Okay, so why there is some repetition of sound? Oh, because of this. Okay, now I'm good. So, as I said, now we are going to stop a little bit with this Margulis Normal Subgroup Theorem and Margulis Factor Theorem. So we are going to do some more dynamical type of statements. Okay. So let me put a problem, a theorem, and then I again will switch the setting, and I will try to convince you that it's pretty much the same setting. So problem due to Furstenberg. Says you take T2 from the circle to the circle and T3 from the circle to the circle. So T2 of x is times 2, 2x mod 1, and T3 of x is 3x mod 1. Okay, so we have these two transformations. Here we identify the circle as R mod C. So this is very well defined then. And hence we can look at the invariant measures for times 2 and times 3. So measures which are invariant for both simultaneously. Okay. Mu such that T2 star mu equals to mu and T3 times mu star mu equals to mu. Okay. Now, if we were only looking at times 2, we have plenty of such measures. So here is 0, 1/2, 1. And the dynamics of times 2 is equivalent to shift onto symbols which is the coin flipping machine, and you have all the measures. You have infinitely more, but at least you have all this guy. Or actually, even make it close here. You have all these measures, which are the standard Bernoulli measures on this system, and this automatically gives you really a huge amount of them. Now, that's just for times 2. Now, what about the measures that are also invariant by times 3? Okay, is any of these measures invariant by times 3? The answer is yes, because for p equals to 1/2, you have the 1/2, 1/2, which is just Lebesgue measure on the interval, and Lebesgue measure for the intervals is invariant by times 3. Also, for p equals to 0, the measure is delta at 0. Delta at 0 is, or for p equals to 1, is delta at 0. Delta at 0 is a fixed point. 4 times 2 is a fixed point. 4 times 3, so you get invariant by times 2 and by times 3. And actually, you see that, well, Lebesgue certainly is invariant for both. And if you have a finite orbit for times 2 times 3, then these finite orbits will carry a invariant measure. And the question of Furstenberg is there any other invariant measure? Okay, so is there an invariant measure for T3 other than convex combinations of Lebesgue and atomic measures? There's several other ways of restating it. One way is if the measure has no atoms, then does it have to be Lebesgue? Okay, that's a reasonable way of stating it. And one of the first main strong results towards it is actually the second main result. The first was by Johnson, I think, and then came Lyon. Well, then came Rudolph, and then came Lyon, or is first Lyon, then Rudolph, then Johnson. But anyway, so what I want to state is Rudolph's theorem that says if mu is T2, T3 invariant, ergodic, ergodic for the joint actions, so this means that T2 inverse of A equals to A and T inverse of A equals to A implies mu of A equals to 0 or 1. And the entropy of T2 is positive. Asking it for the entropy of T3 is no difference in this matter. Actually, if for some K and L, then mu equals to lambda. Okay, so ergodicity, if the other way of restating this problem up here is to ask the measure to be ergodic, in which case it will be either Lebesgue or atomic. That's the problem, or just atomic on a finite orbit of times 2 times 3, and the atomic measures has 0 entropy. So here, instead of asking it to be non-atomic, it's asking a little bit stronger, which is positive Haldor dimension of the measure, or equivalently positive entropy. So that's really the main hypothesis. So we are going to prove this theorem in a different context, slightly different context. Actually, the other proof can be carried into this. Simply I like better to work in T3 rather than some solenoid, but it's the same proof. And then we will make the interpretation of this entropy condition in a very geometric way. And then it should come quite clear where this guy come from. And well, and that's almost state of the art. So there are some improvements to Rudolph, but not the really strong one and powerful one, which is saying what happens for zero entropy measures. So this is a big open problem. If you can do it, you will gain whatever you want, but it's very hard. Okay? So what happens with the zero entropy measures invariant by times 2 and 3. So let's state the theorem we are going to prove. Theorem by actually is Katok-Spatzier, who says the following. We take A and B matrices in SL3C. They do much more general than just this. They do complete abstract version of, still algebraic, but abstract version of this business. And but all the basic tools appear already here in this three-dimensional situation, so enough for us to understand it in this case. There will be later some little bit more complications that are completely trivial in this case, but I can make them appear on purpose in this three dimension, and that's what I'm going to do. So, okay. So I take these two matrices. I assume they commute, because that's the really important thing about times 2 and times 3 here, is that they commute. I look at the induced transformations on the torus, which I still call them A and B. They preserve Lebesgue because determinant is 1, and if not, they still will preserve Lebesgue. So, but anyway, that's other business. And I don't want to have anything trivial, so we want A to the K times B to the L to be different from the identity for every KL different from 0, 0. So I don't want them to have essentially a common power, because then we are talking essentially about iterates of a same matrix, and that's what we want to avoid. So that is all I need here. Let me think, maybe I need something else. Yeah, I do need something else actually, because they will commute. So I want also A or B. In the theorem, this will be automatic, but just to make clear what's the setting, to have non-zero, some non-zero eigenvalue, to have some eigenvalue of modulus different from 1. Okay, I don't want all the eigenvalues to be half modulus 1. So I don't want the following matrix. I don't want these two matrices, okay? So these two matrices would commute, don't have a common power, and are not good for my business. So even though the theorem is very close to be true also for these two matrices, so it's a completely different phenomenon than the one we are going to discuss here. So that's the setting, A and B. Then if mu is invariant, so is A and B invariant, so A star mu equals to mu, B star mu equals to mu, probability. So it's always probabilities unless I say it explicitly. Ergodic, with the same meaning as before, and h star, h mu of x to the k positive for some k and L, which automatically implies this statement here, then mu equals to lambda. Okay, so I still stated separately the fact about the eigenvalues, because as with Furstenberg problem, the big problem is to remove the entropy condition and just to have that it's always lambda or supported on a finite orbit. And if you solve this, it's very doubtful that you would not be able to solve the Rudolph statement. Or, well, the Rudolph is proven, but the Furstenberg original problem. And there are all sorts of problems you can solve if you solve this, actually. So it's really, any of these has a lot of implications, very, very strong implications in this zero entropy situation.
By solve, you mean getting rid of the positive entropy?
Exactly. That's exactly what I mean. So if you can get rid of this positive entropy assumption and get the full Furstenberg problem in either situation, you really won. So we're going to prove this theorem, the Katok-Spatzier theorem, and for this we need to develop a little bit the theory and explaining what we really care about A and B. So the first lemma is really nice. I will let you do it by yourself, so I leave it as an exercise. It's really fun. Okay? Is A and B are simultaneously diagonalizable over R with eigenvalues different from, of course, are real eigenvalues, because I'm saying diagonalizable over R, so it means the eigenvalues are real and are different from plus or minus 1. So in particular, they are in absolute value larger than 1 or smaller than 1, but not 1. So, and the way I really want it to happen is that I have R3 split as E1 plus E2 plus E3, and I have chi I from okay, now comes some painful part, but let me still do it that way, into R. Actually, I can make them go directly from R2 into R linear functionals such that for every K and L in C squared and Bi in this space EI, if I do A to the K times B to the L times this vector Bi, this is plus or minus, depending really on K and L. You can always do something to get rid of it, but let's keep it, e to the chi I of KL times Bi. So this is the eigenvalue for this matrix A to the K, B to the L along this space Bi. Okay? So in this basis, E1, E2, E3, the matrices looks diagonal e to the chi 1, e to the chi 2, e to the chi 3 on K and L depending on the value of K. Okay, and determinant 1 means nothing but the fact that chi1 plus chi2 plus chi3, the sum of these three functionals is 0. And these functionals, the fact that the eigenvalues here are different from 1, has two implications. So kernel of chi I is one-dimensional and irrational, i.e. kernel of chi I intersected with C squared is just 0. That's not really crucial, but it's good to know. And it's not hard to prove. So all this is really not hard to prove. You have to play a little bit, but it's linear algebra. It's fun to do it. So at some point you have to really play, but I suggest you do it and you try. I suggest first you try to prove the same statement for two commuting matrices on SL2C and see how you cannot have this for two commuting matrices in SL2. So actually what you cannot have is this for two commuting matrices in SL2. Okay, so that fails. In SL2 and SL3, you can do it, and the fact that this is true depends heavily on this A to the K, B to the L property here. Okay, so this is very, very important. Of course, commutativity is as well crucial. Because I can extend them, so they will be linear functional. Just to emphasize, they are linear functionals. Okay, so and it's really useful. So we will see. We will make use of it. So we will extend to an R2 action, and then we have them well defined in there. It's not really needed to do the extension, but it's better for all respect. Also for our future use, it is very useful. But it's good to extend to an R2 action because this condition here tells you that the C square action of iterating by A and B will never see the kernel of this chi I. So we'll never make any of this BI frozen. And the key point here, the key game here, is to make this BI or this direction AI to be isometric. So I want E1 to be isometric while E2 and E3 are still moving. So let me draw now the picture here. Yeah, I can do it here, down here. So actually the chi1, chi2, and chi3 are also different from each other. So these kernels are pairwise disjoint. Yeah, maybe I should say this as well. Kernel of chi I into kernel of chi j is 0 for I different from j. So it's really the picture I'm going to draw here. We'll have one guy here and one guy here. Okay, so this is kernel of chi1. And this is kernel of chi3. Okay. And these perpendicular vectors, they will point either this direction or that direction, depending on how you think of chi1, chi2, chi3. And the sum of these three perpendicular vectors will have to be 0 because chi1 plus chi2 plus chi3 equals to 0. And then there is, these are called the Veil chambers. So each of these chambers are called Veil chambers. You have same thing in higher dimensions. Simply you will have more chi i's, and these are the Veil chambers. And we call chi i's the Lyapunov exponents of our dynamics Okay, so chi I are Lyapunov exponents. And I want to emphasize that when you typically have a diffeomorphism, the Lyapunov exponent is a number. In our business, we don't have a diffeomorphism, we have a C-square action. So Lyapunov exponent is not a number, it's a functional. Then, of course, you take one element of the action, you get a number. You take another element, you get another number. And the big news is that these form a functional. So it's not just these numbers are some scattered numbers without relation one with each other. They correspond to a function, a linear function. And as we know, linear function, the kernel is fundamental to understand what is a linear function. Now, for other uses, it's good to think of these guys as, or put the names as being weights or roots, depending on the context we are going to play. Weights is better name for these guys. Not better than Lyapunov exponents, but better in the Lie algebra situation, in the Lie group situation for Lie group actions. This will correspond typically to weights of the corresponding representation. So here we should be thinking, or we could be thinking, these A and B matrices as being a representation of C squared on R3, and this would be the weights of the representation. Even though the theory of weights is better suited for simple Lie group or semi-simple Lie groups. And then in this case, this you take a representation of a semi-simple Lie group, and it has its weights, and these are the weights of this guy. Okay, so I will go again through this when we come back to SLN3, SLNR, and when we work again in SLNR, we just do the corresponding definition of Lyapunov exponents, and I will tell you what are the roots and what are the weights of this guy. Okay. Now, when it comes to understanding these functionals, there are two very important things to a functional. There are more than two, but at least these two. One is the kernel, which tells you where the guy is 0, and then each half space will either the positive half space or the negative half space, depending on which is the guy. So the second information, which is crucial, is who is the positive and who is the negative. So typically we have something like plus minus, meaning that on this cone the first guy is positive. So for the chi1 this is positive, for the chi2 this is positive, and for chi3 this part is negative. Okay, and you need to have not the three the same sign, because the sum of the three is 0. So if two are positive, the third one has to be negative. And if I did this thing correctly, it will be good, but it may not be good. So let's see if I can make it coherent with this assumption. So when I'm here, the first guy switch signs, so the other one didn't switch signs. Then when I jump here, the third guy switch signs, while the others didn't switch, so I get. Then I jump here, is the second guy that switch signs, so I get this, which is the opposite of this, because the matrices here are the inverse of the matrices here. Then I switch here, I switch the first, so it goes to plus minus plus, same thing, the gamma matrices here are the inverse of here, that's why the sign have the opposite decomposition, and here you have plus minus minus, so I guess I did it correctly probably, and that's what you probably have. So these are the sign of these guys, which is telling me, for instance, if I take a point here and n equals to KL, and I consider alpha of n equals to a to the k, b to the l, then this matrix, since I'm here, we have the E1 expanding, the E2 expanding, and the E3 contracting. So in the E1, I multiply by e to the chi1. In the E2, I multiply by e to the chi2. In the E3, I multiply by e to the chi3. Now, this total irrationality tells me that I cannot take a point here. And taking a point here, an element here of the action will be very useful, because if I stay here, then the first direction is 0, while the second direction is expanding and the third direction is contracting. Okay, so this really would make life very easy and not painful, but I cannot assume that actually is impossible. So what I will do now is to build a construction, the suspension once again, construction, but now for this square action, and this suspension will allow me to sit in this line, because I will have an arc square action, and once I have an arc square action, I can put myself inside this line.
So total irrationality means this first property.
Yes.
Okay. And how did you start with plus plus minus there? How did you choose it?
Oh, I had to make a choice, and actually, if I put plus minus plus, probably I will end up with some wrong thing. But it depends on A and B actually. So just make some choice. So there are, I think that any pair of pictures in these settings, because you are in this very low dimension, any pair are isomorphic. So you will start with one of the chambers, which is plus plus minus, and then the next one will have to be like that, and the other side will have to be like that. By some rearrangements of the EIs, you will have exactly this picture.
And why don't you have plus 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 anywhere?
Because the sum of the three guys is 0, which is determinant 1. So you cannot have all expanding. Good. Okay. Very good. So we go to the suspension now. Maybe I can do it here, I guess, no?
So this is at the Lie algebra level.
This essentially would be at the Lie algebra level, and that's exactly in the case of Lie algebras and simple group representations. This is how the Lie algebra representation is working, essentially using the bracket, which is by the multiplying by the chi-i, and then you exponentiate this to the Lie group, and you get this a to the k b to the l applied to bi is e to the chi I times bi. So one thing I want to do now first is getting rid of this plus minus. This is just take a finite in the subgroup. So instead of using a and b, use a squared, b squared. So if a had a negative eigenvalue, a squared will have all eigenvalues positive, b squared will have all eigenvalues positive, and that's it. Okay, so this will mean that all the eigenvalues of a to the k times b to the l are positive, and we can get rid of this plus minus, which is just a pain. And it will not change anything. So mu is still invariant and ergodic. So ergodicity, maybe you have to argue, make some ergodic decomposition, you still will have some entropy, positive entropy for both guys, and move on. So I'm proving in an event that the measure is Lebesgue. So that will kill anything else. So I will assume then that the eigenvalues are positive. It will not show up actually very explicitly, even though it is. I will try to emphasize when it comes to the use where we were using that the eigenvalues are positive and not negative.
Also for this Katok-Spatzier, is it important really that these are irregular matrices? Because in the Rudolph Theorem for times 2 times 3, it's not.
No, it's not important at all, but you can always assume it. So what you do is you do the inverse extension, the invertible extension. And that's why is really the very, very, very same proof. You go to the invertible extension of times 2 times 3 is so you have a semi-group action, so it's natural times natural action. So the invertible extension now is not for times 2 and or times 3, is for both simultaneously. So now you will have a C-square action. So you will get a solenoid. But this solenoid is very algebraic in nature. Actually, if you allow to use yourself to use p-adic, is pretty much the same as we have here. Is dyadic times 3-adics times R. So instead of, so it's three dimensions, but it's 3 dimensions of different nature. So it's 3 different fields, but it's still three guys. And then you will have these 3 Lyapunov exponents, and the rest of the explanation is exactly the same as this. So you have chi1, chi2, chi3. Chi1 is log 2, chi3 is log 3, and the other is whatever is the rest, because the sum of the 3 will be 0. Well, whatever. So it's log 2 and 0, log 3 and 0, and the rest is whatever it has to be. So, so these are functionals on R2. So yeah, the perpendicular to this function is log 2, 0, 0, log 3, and minus log 2, minus log 3. So that's are the perpendicular to these 3 functions. Whatever, you have to make identifications and blah, blah, blah. But the really main difference, and which actually makes the life a little bit simpler for Rudolph than for this, is that once you want to the solenoid, you don't have this property here. So this is not true anymore, 4 times 2 times 3 when you go to the solenoid, which means that you have a guy which freezes the chi1, which make it isometric. And then you don't need to go to suspension. You can actually argue directly there. And that makes life much, much simpler. Well, not much, much simpler, but a little bit epsilon simpler. Okay? So this fact is actually not really of help, neither is a pain. So it's just you need to work with this suspension. But other than that, it's not so important for the argument. What is important in the discussion I'm going to write is not crucial, because a lot of things can be done without this hypothesis, is that the EIs are one-dimensional. This is quite important. So again, if this were not true, a lot of things can be done and a lot of things are true. And we are going to play eventually and try to discuss a little bit what happens when they are higher dimensional. But this implies you have to work a little bit more. Second thing, which is even more crucial in this situation, and if you don't have it, still you can do stuff, and we are going to discuss what we can do, is the fact that each direction can be separated from the other in the following way. So I can make the third direction at the only contracting guy, while the other 2 are expanding. Okay, so this really simplifies the problem a lot. So in other situations, that's not possible, and then you have to work harder. And there are other consequences of this that eventually we will have the time to discuss it, which also simplifies a lot. So really, this 3-dimensional is a oversimplified situation, but it's perfect to start understanding how the mechanism goes. And then we will try to expand and see what we can do if we don't have it, and what's the use of doing whatever else without having that. So I plan actually to try to extract 2 main statements out of the proof of this, which try to make them very abstract. And once we have this very abstract statement, these will be our building blocks to prove the factor theorem and whatever else we want to prove. Okay, so suspension first. So we do our suspension. We have alpha. I already put the name alpha. Alpha of n is the c-square action, and we can, I'm going to call m alpha. It would be R2 times T3 under the relation where, as before, we take T, we take X, and we relate it with T plus N alpha of minus n of x. Okay, so it's the same as before. We did it for the group gamma, lattice gamma on the group G. Now we are doing the lattice C square on the group R square. And we have the suspension action now, then R square on M alpha. And as before, these fibers over T2, which is R square over C square, with the corresponding R square action here, which is the standard transitive action on T square by just multiplication or addition. Okay. Now the fiber here is T3. Okay, so over each point here I have a T3. This is a solved manifold. Actually, M alpha is a solved manifold which has this fiber T3 over this T square. So the solvable Lie group which is behind is R2 semi-direct R3, which whatever twisted addition coming from this expression. Now, in this 5-dimensional manifold, I have in the fibers a splitting E1 plus E2 plus E3. So I have M alpha is 5-dimensional, and the tangent at any point Tx of M alpha splits as the tangent to the orbit, which is the R2 part, sum the tangent to the fiber T3, and the tangent to the fiber has a splitting E1, E2, E3, which is essentially the same splitting I have here, R3 equals to E1 plus E2 plus E3, so I'm having it over there. So this guy is inherited from the fact that the cover, in this case is the universal cover actually, of M alpha is R2 times R3. So this goes to this, and that goes to that. So that's what happens at the tangent level. Now, similar thing happens at the manifold level, the same as with the torus T3 and R3. So let me just do a 2-dimensional picture because there is no need to do, well, let's do the 3-dimensional picture. So
here, lowercase t is a pair of numbers.
yes, lowercase t is an element in R2. And this is an element in R3, in T3 actually. You could do it in R3 as well and make some identification. So on T3, we have these 3 directions that I hope you see. I will not be able to see it, but I hope you do. Then I'm sure I will not see it. So okay, this is E1. I'm doing it the wrong way, no? That's correct. And this is this, no? E2, E1, and E3. Okay, and you have the parallel foliation. Good. To these guys, and I have the parallel foliation to this guy, and I have the parallel foliation to this guy. So I have these three parallel foliations there on T3. So well, they are on R3 and they descend to T3 naturally in a good way and generate these three foliations. And not only that, they induce as well foliations on the fibers of M alpha. So I have these three foliations on M alpha by one-dimensional. So one-dimensional foliations on M alpha. Okay? I can pair them as well because I have as well E1 plus E2, E2 plus E3, and E1 plus E3. So I have these bundles are invariant and they also induce foliations. And these foliations not only exist and it's just the pairing of them two, they correspond here, they have a very dynamical meaning, which is the A1 plus A2 is the unstable foliation for elements on this place. And well, next, the A2 plus A3 is the stable foliation for these guys, and as well as the unstable for these guys, and so on. So all this info is important and useful. And I have all this info up here. And so once I know all this, I will have that. So I will put a name, Wi of Tx is the name of the leaf where it has to belong. And I also have this Wij of Tx when I put the pair of foliations, I put them together. Now the big lemma, or the main lemma, or an important lemma, or maybe I should say something else. Yeah, let me say epsilon more. So the same that as happened in T3 and R3, I have a natural distance function on this M alpha, especially on the fibers of this guy, and even more importantly, on this inside this Wi, there is inherited a natural distance function. Okay, coming from the Riemannian metric on the manifold I will put there. So here you put, so it's not R2 times R3 as a Riemannian manifold, it is as a topological manifold, but not as a Riemannian manifold because it's a semi-direct product, but still you can put whatever right or left invariant distance. I guess is the way I wrote it is probably some left, if I'm doing this is right. So right invariant distance on this, and this is the natural Riemannian metric you will put, which will make all these tori that appear there look at the standard flat tori being the quotient of R3. And that's the Riemannian metric you want to think about, and that's the Riemannian, the way you are going to measure distance inside the Wi by inheriting this Riemannian distance. Okay, so what is the importance of thinking of this distance is that I have the fact that in this R3 picture, in the direction E1, I multiply by e to the chi1. In the direction E2, the distance gets multiplied by e to the chi2. And in the direction E3, the distance gets multiplied by e to the chi3. And I want this same to happen now here in the Wi. And that's what the lemma is going to tell us. So for every Tx in M alpha, there exists H sub Tx from R, actually Hi. Okay, let me just call it P. So P is Tx, but I don't need to really, who is T and who is X is not relevant for us. I have this Hi for from R into Wi of P. Which is my identification of this Wi with R using the distance I was talking about. Okay, and what I would care about this is the following properties. So this is inside M alpha, of course. So the dependence of F, so oops, I should say it first, HP is C1 is actually infinity, but I only care it being C1. Second, P, so P in M alpha, this in embeddings of R into, or embeddings actually, into M alpha. This, and here is with this convergence over compact subsets is the topology I'm putting here of the guy and the derivative of the guy. This function is continuous. So that's the first two things I care about it. The third actually doesn't have to do with HP, but allows me to make sense of 4, which is alpha. Okay, did I wrote alpha? No, yeah, I told alpha. Alpha of T will map Wi of P into Wi of alpha T of P. And the whole goal of this lemma is to tell you how this guy looks in the HP coordinates. Okay, so this HP is some sort of charge, if you want, for the Wi manifold, and I'm going to tell you how this looks like on coordinates. I guess I should move here. Okay, I can move here. So 4, let me do the diagram, and then I write it explicitly. Wi of P, Wi of alpha T of P. Here I have this coordinate R, H sub P, I. Here I have this coordinate also R, H, alpha T of P, I. Here is alpha of T. And down here then I will have something that I will call alpha sub P of T. Okay, and alpha sub P of T applied to X is nothing but e to the chi I T times X. Okay, so that's really what I care about this. Do I need something else? yeah, I will need some fifth property, which is actually the consequence of the previous ones. One have to prove it, of course, but it's not, in this particular case, actually, shouldn't be very hard to convince yourself that it is true. So far, whatever I wrote in this situation follows directly from doing this careful identification of R3 with the universal cover of the fiber T3 of them alpha. Okay, so that's all you are thinking. So an R is the natural identification of this WIP with EI and then with R. So that's all I'm doing here. And that's why these 5 shouldn't be so strange, but let me do it. So if Q belongs to Wi of P, then if I do HPI compose HQI inverse, so I look at this change of coordinate from R to R, this guy compose HPI at X is X plus TPQ, where TPQ is plus or minus, depending on how things are working, the distance along the I direction from P to Q. Okay, so it's just translating from P to Q. That's what it is. So the fact that this is really the distance is not so relevant. It's just adding to the knowledge. So that's all we care. Okay. So the same thing happens directly if I only think in the torus T3, then all this even looks more trivial. The only problem is that I cannot make chi I of T to be 0 if I'm working on T3. But if I'm working on M alpha, I can make this chi 1 of T equal to 0. And I really very badly want chi 1 of T to be 0 to be able to do that. Okay, time is almost up. Yeah, probably the next thing I will have to do will be too long, so maybe it's good to stop here. So I hope you got the picture of what we care. So we have this 5-dimensional dynamics. It is 2 dimensions from the orbit. Along the orbit, the dynamics is trivial. It's just translation, R2 translation, really. Nothing is happening. And projects onto this torus T2 base as natural translation. So nothing is really happening there. So then you have this R2 orbit. And perpendicular to these R2 orbits are these fibers, which are the same as T3. And on these fibers equal to T3, you have these 3 directions, 3 foliations. And on each of it, you are multiplying by the corresponding chi I. So when you flow in the T direction, you are moving there. You have all your guys inside your R2 orbits, which move parallel to you. And then in the fiber direction, you have some guys that separate from you hyperbolically and other guys that are convergent to you hyperbolically. And if you happen to be in the T which belongs to the kernel, let's say you are moving and you belong to the kernel of chi 1, then what you will have is that the guys which are in the first direction are still parallel to you in the direction of the torus T3. The guys that are in the chi 2 direction will be separating from you exponentially, and the guys which are in the chi 3 direction will be converging with you exponentially. But the guys that are crucial are these guys that are following you in the future. Okay, so these are really the guys we want to explore, because since they are going to go with you for the rest of the life, there will be a lot of information that we should be able to share one with each other. Okay? So that's the guys we are going to explore. And this is where the information will come up. So, but we are going to do that on Monday. Okay. See you on Monday.